Hi, I'm Dr. Brad Musil, and this is Lecture 4 of Logic and Critical Thinking. This is the first lecture in the second section of the course. As I've been alluding to throughout the beginning of the course, this is, at least in my opinion, by far the most difficult section of the course. We'll be doing things that can be pretty tricky if you're not used to them. Things like Venn diagrams, which we'll talk about in this lecture. And then the next lecture as well, we'll be doing things like truth tables in the truth functional logic, lecture 5. In that lecture, we'll be doing some tricky things as well. So this is definitely a section that you'll want to put on your thinking caps. You'll need your best to put your best effort forward. This is one of those things that can be really tricky at first, or what we talk about in these two chapters. It can be really tricky at first, just like when you're learning things in math. It's not easy at first. You gotta do the homework, right? You gotta work at it. But with time, I think just like math, if you put forth the effort, doing Venn diagrams actually becomes pretty easy once you learn the basic conventions, which we'll detail in this lecture. It does become pretty easy, and then it's awesome to employ when you're trying to assess, why we're talking about them here, right? Trying to assess arguments because it does give you a nice pictorial representation of what's going on in the argument, and it offers this and a means to assess the argument. So there's a reason why we're talking about all this, but it is pretty tricky stuff when you're first learning it. But again, I want to emphasize that although it is the most difficult material that we'll be covering throughout the semester, throughout the course, it's still something you can not easily, but you can master with the due effort required. So I guess I just wanted to acknowledge the difficulty of some of the stuff we'll be covering here at the outset, but then also emphasize again that it is something that we should all be able to master with, I don't know if master is the right word, but be able to do with relative ease as long as we put in the practice and so on. Okay. Don't want to belabor that too much though, but kind of a related point then as well is I recorded extra lessons videos a couple years ago on specific elements of what's discussed in this lecture, or also then if you're taking the course, right, chapter 9 of our textbook. Discussed, I recorded specific videos, for example, so I called them extra lessons. I will provide links for these additional videos and these additional lessons in this video at the bottom, okay? But I talked about, for example, in detail, translating into standard form claims, right? I have a whole video on that. In fact, that's extra lesson A. Extra lesson B is all about Venn diagrams. Extra lesson C, the square of opposition. Extra lesson D, categorical operations, where I'll go through conversion, obversion, contraposition, and so on, in much more detail than what we'll do in this more general presentation of all this material. And the final extra lesson is using the rules method, right? So extra lesson E, I'll go through in much more detail, talk about the rules method for assessing categorical syllogisms, right? So point being here that, again, I am offering a lot of resources, and so acknowledging, right, that some of this is pretty tricky, go ahead and dive into those extra lessons, right? If you still feel a little confused maybe after what we talk about in the more general lecture 4 lecture video here, dive into those extra lessons where I go into more depth with respect to each of those different topics, and also go through several examples in each of those videos as well. So again, I provided the resources for you. It is something that can be accomplished, right? Figuring out how to do these Venn diagrams, figuring out how to translate seemingly anything that's said into one of these 4 standard form claims, which you have to do for what we're doing in this chapter or this lecture. Right? I think that's all I wanted to say here at the outset. So, what we're going to be doing, and we're going to be unpacking a lot of stuff here, right? We're going to be talking about the general notion of categorical logic. So, this is what we're doing in this second section, right? Is we're taking a closer look at deductive and inductive arguments. Okay, so in the first section, we kind of carved out in general what we're doing in this course, and we talked about what arguments are in a general sense. Well, now in the second section of the course, we're taking a much closer look at those 2 basic types of arguments, deductive and inductive arguments, beginning with deductive arguments. So these first 2 chapters or lectures in this second section, okay, so let me reiterate, lecture 4, categorical logic, corresponds then, if you're taking the course, to chapter 9 in the textbook. What used to be, if you have the 10th edition, right? So that's the 13th edition of our textbook. What used to be chapter 8 in the 10th edition, the previous edition I used. And the reason why I'm mentioning that is because in those extra lessons, I do refer to like example such and such in chapter 8. Well, that would be most of our examples in the 9th or in the 13th edition are the same ones remain from the 10th, but they're in different spots, and it's a whole later chapter. It's chapter 9 instead of chapter 8. So hopefully that makes sense. But wanted to mention that. So what we're doing, right? We're unpacking a lot in this this chapter or this lecture. We're talking about what categorical logic is in general. We'll go through and talk about the standard form claims, right? The 4 basic standard form claims, which then you can do so much with, right? And we'll talk about how you can translate seemingly anything that's said, right? As tricky as it might be, especially when you're first beginning, seemingly anything that's said in ordinary everyday language into one of these basic standard form claims. Okay, and then we'll talk about Venn diagrams, how those can represent standard form claims. We'll talk about how to use Venn diagrams to assess, categorical syllogisms, different types of, deductive arguments. We'll also talk about the rules method. I mentioned an extra lesson E that I provided. I'll go into this in more depth, right? But we'll refer to as well the rules method for assessing categorical syllogisms. We'll talk about what a categorical syllogism is as well. So, as I mentioned, a lot to unpack here in lecture form. The general topic, though, is this idea of categorical logic. So, why don't we go ahead and dive in then, so to speak. Oops. So, turning to slide 2 of the lecture notes, right? We'll talk about the basics. So I've mentioned in prior lectures Aristotle and his continued influence throughout the history of philosophy, particularly or especially, you might say, in logic. And this in particular is an example of his continued influence. A lot of what we discuss here dates back to him and what he introduced, 2,000 plus years ago. So Aristotle is certainly a huge figure in philosophy, and especially in our particular branch that we're discussing, logic and critical thinking. Okay. Well, what is this idea of categorical logic? So we know, as I mentioned a moment ago, right? We're examining in more detail now in this chapter or lecture, and then also lecture 5 when we talk about truth functional logic, right? We're talking about deductive arguments or arguments that are presented. What happens if we take them in a deductive sense? Remember, the identifying feature of a deductive argument is that the conclusion is thought to necessarily follow given the premises. Okay? So we're dealing with that type of reasoning. And categorical, so it's deductive, and categorical logic in particular deals with relationships between categories or groups of things. Okay, we'll say more about this in a moment. Right? Classes, anything you can sort of describe as a type of thing, right? That can be a category or class. Fire trucks, red things, people named Brad, right? You can go on and on and on. Anything basically you can think of that identifies a type of thing, that's a category or a class. Right? And so what we're doing then, or what we're up to here, is we're saying what happens when we take what someone says, right, that has to do with various classes or types of things, and analyze what they're saying, provided it's like an argument, right? What happens when we analyze it, right, in this deductive sense, right? And so we take what they say and we ask ourselves, does the conclusion have to follow given the reasons that they've given, right? So what we're doing here then is we're going to go through a way to sort of do that, right? To be able to take what they've said and, again, analyze it as if it's a deductive argument, whether they intended it to be or not, right? What happens when they say things like all men are mortal, people named Socrates are mortal, so on and so forth. Well, what happens when we take whatever they say, right, and construe it, right, as if they're meaning to prove their conclusion, right? What happens when we take that, what they say, and try to analyze it as such? Is it in fact the case that the conclusion has to follow, right? What we're going to talk about is going to enable us to assess that sort of thing, right? To figure out, as we'll say, right, whether it's valid, in some sense a good deductive argument, or invalid, hence a bad deductive argument. As the editors or the authors of the textbook define categorical logic on page 258 of our textbook, quote, it's logic based on the relations of inclusion and exclusion among classes or categories as stated in categorical claims. Okay, and we'll talk more about inclusion and exclusion here in a second. Okay. So again, we're talking about categories, And generally the idea is there's a sense in which what's expressed, right? There's this sense that we're including one category in another or excluding and saying, it doesn't belong in some sense. This will make more sense as we proceed and talk more about that sense of inclusion and exclusion. But again, we're dealing with categories or classes of things and their relationships to one another. So a categorical claim then, as they say in the 10th edition, page 255, quote, says something about classes or categories of things, end quote. And as they say in the 13th edition, page 258, why are we doing this? Quote, it's useful in clarifying and analyzing deductive arguments, as I've been suggesting. Okay, so turning to slide 3, as I've intimated, right, what we're going to be doing basically is a lot of what we're doing in this chapter or this lecture, what we're going to be doing is translating, we're talking about how to translate seemingly anything that's said in an everyday sense, right, to one of these basic standard form claims, okay? And the first thing we have to emphasize here is it's got to be a perfect match. Right? So to do everything that follows, and that's another thing worth pointing out, right? You have to understand one thing to then understand what's going to come later, right? So make sure you understand this, and then before you'll be able to understand, right, diagramming these, right? You've got to make sure you understand the basics upon which all this other stuff is founded, okay? But you have to match up perfectly here, right? It has to be match up to one of these forms perfectly. So you might have like, Beavis is a really cool dude. You have to get that average everyday sentence into one of these forms, right? So if we were going to do that, for example, Beavis is a really cool dude. That doesn't look anything like, right, at first, anything like one of these 4 standard forms. Okay, but if we were going to try to translate it, then we'd have to say something like, and again, I'll talk about how this process works in more detail as we proceed, but I'm just trying to give you an example of what the translation process looks like here. We would say something like, and it's also awkward when you're talking about one person, because one of the points we'll emphasize here shortly, right, is these classes or categories, they deal with, they're plural, there's more than one, right? So, and they talk about this in the textbook, right? When they give an example, I think I can reference it here in a moment. Talking about Aristotle, you have to change that to get it into standard form. You'll have to change that and to make it sound a little bit different, and it can sound a little funky too, right? So it'll be something like all people. You could say like named Beavis or identical with Beavis, something like that. All people named. I'm sorry about the space here. All people named Beavis are, we'd say, cool. You can't have cool dude. That's singular, right? So we'll have to switch that to cool dudes, right? So that, what we started with, Beavis is a really cool dude. We'll translate then, maps up to one of these, right? Almost, again, I can't even think of anything. I mean, I'm sure there's stuff that can be said that you can't get to one of these forms, but seemingly everything I come across, right, even as weird as it might sound at first, you can get into then a standard form, right? So Beavis is a really cool dude. If we were to try to put this into a standard form claim, we would translate it to all people named Beavis are cool dudes. Okay, so we have, again, plural, and it's a class or category of things in both of these slots. Okay, so the point here, again, I was trying to make a more general point that, again, anything that's said can be translated into one of these basic forms. Okay? Or let's say we started with Beavis isn't cool. You would translate that then into what we'd call a standard form E claim, right? All people, or sorry, no people named Beavis are people that are cool or cool dudes, or however you put it. But so if there's that exclusion, going back to that concept, right? If this was Beavis is not a really cool dude, again, we could translate into standard form. It would just look different, right? We would be using a different standard form claim. Let's see. No people named Beavis are cool dudes. Okay, and then we've represented that sentence. Okay, so Again, whether they're including or excluding, okay, we can then represent what was originally said in one of these basic standard forms. And this will make a lot more sense as we proceed and go through more and more examples and go and check out those extra lessons where I hammer, example after example I go through on all these various concepts. So what are these 4 standard form claims? As I mentioned on, slide 3, you're going to have to just kind of get these ingrained in your memory, okay? So what are they? We have the standard form A claim, all blank are blank. And I'll explain these little squigglies, why some of these are squigglies that's there for a reason, okay? And why some of them are just regular blanks. That means something. I'll reference that later in the lecture, okay? So standard form A claim, all blank are blank. Standard form E claim, no blank are blank. Okay, standard form I claim, some blank are blank. So, some animals are cats, you might say, right? Something like that. And then O, some blank are not blank. Okay, some animals are not cats. So, whatever you're saying, for the purposes of what we're doing in this chapter, you are going to need to be able to translate something originally said into one of these 4 standard forms. Okay, and it has to be a perfect match. You can't have any other additional words in there. Whatever else you have has to be just the category or class that would go into the blanks. Okay. Okay. Let's move on to slide 4. So a lot of times, and this was the case throughout the chapter as well, you'll get in these standard forms the subject term. So this is where the subject will go and the predicate, what's called the subject and predicate, and you'll get them referenced by the letters S and P. And so that's what I'm acknowledging on the top of slide 4. And we use S and P just because in general, all right, this is where the subject of the sentence goes, and this is where the predicate goes. Okay? So we're saying something, right? We're qualifying something about this category or class using this other category or class. Okay? We're including or we're excluding, okay? Based on what's being said, basically. So I mentioned, note the note on the bottom of slide 4. Again, both subjects and the predicates have to be noun or noun phrases. Well, I guess that's a separate point from my first point, right? That they have to be plural, or we're dealing with more than one. That's why Beavis, right? We can't just put Beavis. It's got to be, right? It wouldn't make sense, right? All Beavis are cool dudes. No, it has to be all people identical with Beavis or something like that. But then as I note, right? So plural has to be plural. But also we have to have nouns or noun phrases. And so what we mean there is you can't say, is this an example they use in the book? Some snakes are poisonous. That's not, poisonous is not going to work. An adjective doesn't work, right? We need to, so if that was said, you know what, I'm going to give myself some more room here. Some snakes are poisonous. Okay. That's actually pretty close to standard form in itself, right? If somebody just told us that, that is actually almost already in standard form. But this we have to work with a little bit. So this is going to translate what we call the I form, standard form claim, right? We'd say some snakes are, and you can tweak this kind of however you want as long as it's applicable and meets these criteria, right? That it's plural and it's a noun or noun phrase. So you could say like, are poisonous creatures, or you could say poisonous snakes. You could just use that again, poisonous snakes. But one way or another, it's got to be a noun or noun phrase. Adjective by itself, not going to work. Okay, so this, very close to standard form, not quite good enough. So we'd have to tweak it a bit and say some snakes are poisonous creatures or poisonous snakes, right? So that then, you'll note, does map up perfectly to the standard form I form, okay? And it does have, again, noun and noun phrases in both of these blanks, okay? Whereas this, originally, this was not a noun or noun phrase, that's an adjective, okay? All right, let's move on to slide 5 here. Duh. So the first note right on the top of slide 5, we've been talking about this already throughout the lecture, but you got to get used to translating. That's what we're doing right in this lecture. Translating these ordinary everyday sentences into one of these 4 standard form claims. And as I've been suggesting quite a few times now, it is doable with practice. But as I point out on slide 5 here, sometimes it can be particularly tricky, right? There are instances we've already alluded to some, or I've alluded to some, right, where you're dealing with one person. Well, that's not going to work for a standard form claim. You need more than one, right? So as awkward as it might sound, you got to translate, Aristotle into people identical with Aristotle, something to that effect. Okay? Also, when you're dealing with times, they talk about this in the text, and so I give you examples and quoting the text on the bottom of slide 5. Talking about times can be a little tricky. So if we started with, for example, I always get nervous when I take logic exams, and that's quoted from page 263 of the text. So let's say that was our original, what somebody said to us, right? I always get nervous when I take logic exams. Okay. To me, that sounds kind of like an A claim. They're saying something about all the times they're taking logic exams, right? Namely, there are times they get nervous. So it's going to translate into, as they say on page 263, quote, all times I take logic exams are times I get nervous. So let me put that up there just so you can see that. So what we translated it to, all times I take logic exams. And I want to put it all here so I can emphasize this is all one class, right? Times I take logic exams. All times I take logic exams are times I get nervous. Again, all one class, right? So we're talking about classes or categories of things, okay? It might be people, vehicles. In this case, times, right? All times I take logic exams. So this is a class. Times I take logic exams. Here's another class. Times I get nervous. Okay? And so we've translated that original sentence, I always get nervous when I take logic exams, into a standard form A claim. All times I take logic exams are times I get nervous. And before I forget, I know I had this here somewhere, I think. It's got to be, I think I have it somewhere, present tense too. So, right, so if something's said in the past tense, you have to get it, and that's doable too, right? You just have to then tweak it so that that it's put in present when you get in the standard forms. So let me try to think of an example here. I had in the extra lesson, I gave an example, I think, of like Tom Brady's throws. So let's say we're talking about in the past, right? All his throws this past season, all of his throws last year were great. So we're talking about something in the past originally, right? All of his throws last year were great. His being Tom Brady's, okay? So how do we get this, which is dealing with something in the past, right? We got to also get in the present tense. Okay? That's the point I'm trying to make here. Well, it's a pretty good indication we're dealing with an A claim again. So we want to try to capture this idea of his throws last year, right, as a class. Okay, so let's say all be something like throws Tom Brady, or you could say Tom Brady made last year are, so now we've got in the present, throws that were great. So all throws Tom Brady made last year are throws that were great. So we've captured what was said about the past. Again, it can be a little awkward, right? But it maps up perfectly to the A form, and it's in the present tense. So all throws Tom Brady made last year, that's a class. Throws Tom Brady made last year, that's a category of things. All throws Tom Brady made last year are, another category of things, throws that were great. Okay, so hopefully that kind of makes sense. Again, going back to slide 5, we're kind of talking about tricky scenarios or tricky instances, right? So a lot of times it can be relatively straightforward once you kind of get used to it. But these times where you're talking about the past or one person or times in general or places, those can be a little tricky. And so that's what we're doing on slide 5 here, is going through some of these more difficult instances. So I like the example, the next one I quote from the 10th edition, on page 260 from the 10th edition. They gave an example. So someone says, quote, "He makes trouble wherever he goes." Okay. Well, how would you translate that? You'd say something like, quote, "All places he goes," so category, places he goes, "are places he makes trouble." Another category, places he makes trouble. Okay, there's the same point we've made, right, about, I made it with respect to Bevis, and I talked about how they mentioned it with respect to Aristotle, so I mentioned that at the bottom of slide 5. So, somebody says, quote, "Aristotle's a logician," end quote, you're going to need to then translate that to a standard form. It would be something like, as they point out on page 265, quote, "All people identical with Aristotle," or you could say all people named Aristotle, or something along those lines. Or I guess it would have to be identical with, because people named Aristotle wouldn't be capturing specifically, right, the person they're trying to identify. So I should be more precise there. So as the authors put it, that's the correct way, right? All people identical with Aristotle are logicians. So this should also probably be switched, right? No people identical with. And hopefully it makes sense why I'm making this point, right? Because it's not good enough just to be named Beavis. Okay? The person saying this didn't want to say something about all people named Beavis. They wanted to say something about this particular Beavis. So no people identical with Beavis, this particular Beavis, are cool dudes. Okay, so let's move on to slide 6. So once you kind of start having the standard form claims down in your mind, and you kind of get comfortable translating most of what's said in an everyday sense into the standard form claims, then we can start talking about Venn diagrams. Maybe you've heard of Venn diagrams. To be honest, I hadn't really heard too much about Venn diagrams until I dabbled with logic. But other people, they come into the class and they'd heard of Venn diagrams, and so maybe you have, or maybe you haven't. But basically, it's a way to represent what's being said pictorially, usually using these circles. Okay? So as I mentioned on slide 6, and so I posted it, or copied it, pasted an image there at the top, trying to capture all the what the Venn diagrams look like for all the standard form claims. Okay? And so I'll go through each of these in turn and sort of talk about what's going on when we use a Venn diagram to represent then what's being said in the standard form claim, right? So what we're doing with this diagram is portraying the underlying structure, logical structure of what's being said. Okay, so why do we have 2 circles? Well, because we have 2 categories of things, right? So if I'm illustrating a standard form A claim, so standard form A claim, right? I need 2 circles because I'm representing 2 different categories or classes of things, S and P, right? So, and again, these are, I'm going to start talking a little bit about our basic conventions and things. What I mean by that are things that you need to just do, right, and copy. And there's different ways of doing it. So, for example, when we get into using Venn diagrams to illustrate categorical syllogisms, we'll be dealing with 3 classes. Well, some people, some textbooks, they'll have you put the 3rd circle up here. No, for us, we're putting what's called the middle term. More on that later. We're putting it down in the center and down lower and in the middle of these 2. Okay, so some people use shading to represent, some logicians use shading to represent one thing. Well, we're going to be using it. This is what I mean by basic conventions that you have to familiarize yourself with. We're going to be using it to mean a very specific thing, and so you need to make sure you stick to these conventions. Okay, so we are representing 2 different classes because we're saying something about 2 different types of things, right, in the standard form claim. Okay, So as I mentioned in the bottom of slide 6, I already mentioned that, right? The circles represent these classes, but then also shaded areas, right? What are those going to represent? Areas where there are no members, okay? So we're indicating not possible to be, right? If there's an area shaded, it's not possible, nothing exists there, okay? An X, conversely, means there is at least one thing there, okay? And so I'll go through, that'll make a little bit more sense here as we proceed. So let's go ahead and go through each of these in turn. I'm going to go ahead and do that. So what does the Venn diagram for the standard form A claim look like? Well, we're told all S are P. So if it's a member of S, if it's an S type of thing, it also has to be a P type of thing. It's not, in other words, it's not possible to be A or S and not also be P. So how do we represent that? We know shading means nothing's in there, right? Let's use that. It's not possible to be an S and not also be a P. So if it's an S, it also has to be a P or in here, right? So we want to shade out, exclude this from the realm of possibility, this area of the circle, of the S circle, because it's not possible to be out here, given what we're told, right? All S are P. It's not possible to be an S and not also be a P, okay? Hopefully that kind of makes sense. Now, let's see what a standard form E claim looks like with a Venn diagram. Here we're told no S or P. It's not possible, excluding the possibility of being an S and a P. One thing I want to mention, and I have it here somewhere, I think. One assumption, convention we're using, is that these are not empty. There will always be at least one member in these classes, okay? And so that'll matter more for what follows, okay? But I wanted to point that out while I'm thinking about it, okay? So we're told it's not possible to be an S and also a P, right? So we're going to actually shade out this portion this time because you can't be both given what's said here. Okay? No S or P. So this represents what we're being told in a standard form E claim. It's not possible to be S and P since no S or P. Okay. All right. What does a standard form I claim look like? Whoops, just not the S and P up there. Okay. So here we don't do shading, rather we use an X. Okay. So we're told some S are P. Okay. Not necessarily all of them, but they're, and this kind of gets into the next slide, slide 7. You know, it's not all of them necessarily. It might be, right? But the person telling us is just saying, hey, look, some. There's at least one, maybe 20, maybe 20,000, maybe 5 billion, right? But there's at least some S that are P. So how we represent that using a Venn diagram is we use the X and X. So here in this instance, we're being told that there's at least some S that are also P, right? So this part is representing the possibility of being both, right? I should have said that from the outset. This part of the S circle is representing the potential or possibility of being an S but not also a P. And this part of the P circle, or red, is representing the possibility of being a P but not also an S. Okay, so we have 3 possibilities here that we're representing in some sense. Hopefully that made some sense. So we're told with an I standard form claim, some S or P. So what we know, right, what we want to represent is there's at least one thing in there, okay? Again, maybe 5 billion, but we know there's at least one there. That's what the X tells us, and that's all it tells us, is that there's at least one, maybe many more, but at least one member that's here, okay? So some S are P. Maybe some S aren't P. We don't know, given what's told here in a basic I claim. But what we do know is that, hey, some S are P, okay? What about O? Kind of similar, but here we're told some S are not P. So rather than putting an X here, we know, and maybe there are some S that are P, right? But what they're telling us with an O standard form O claim is that some S are, in fact, not P. We know there's at least one, maybe 25 trillion S's that are not P, okay? Okay, that's the basics of the Venn diagram, like illustrating standard form claims using Venn diagrams. As I mentioned on slide 7, for the purposes of translating into standard form, right? If something said like hundreds, one, several, most, any indication that there's at least one, okay, and not all, because then that would be A and not I, right? But any indication, this is the point at the top of slide 7, right? Any indication that there's at least one, right? Whether it's hundreds, one, several, most, many, that's all going to be indicative, right, of an I claim, right? Standard form I claim. And this should all be translated, as I mentioned, top slide 7, as, again, standard form I claim, some blank are blank. Okay, so this is where I officially talked about it in the lecture notes, the idea of affirmative and negative claims, right? And hopefully that's kind of just intuitively obvious, right? Here we're including, right? We're saying something, right? We're including the S with the P, right? Whereas here we're excluding. We're not allowing, going back to how we illustrated, right? We're not allowing S to be P, if you will. Okay? So no S or P. It's not possible to be here. We're excluding that possibility. No, not possible. And then also same idea here, right? We're excluding at least the some S that aren't P from being P, right? So these are considered affirmative or inclusive, and these are considered negative or exclusive. So again, plus equals affirmative or inclusive. Negative equals negative or exclusive. Okay, moving right along. So this is one of the square of opposition. Pretty cool, actually, this idea of the square of opposition. I think we're done with this general stuff. So moving to slide 8, that is, we'll start talking about the square of opposition. Pretty cool in that, again, once you kind of, for a lack of a better way of putting it, memorize kind of the square and some of the relationships, it's pretty cool what you can kind of deduce from just knowing one thing. That'll become clear as we go through some examples here. But so we have this idea of the square of opposition. Again, this is slide 8. And the basic idea, as I mentioned on slide 8, you just have to kind of commit this to memory. The basic idea is if we know something about the truth value of one of the standard form claims, that's actually more like a rectangle. Maybe we should call this the rectangle of opposition. The idea is if you know the truth value of one of the standard form claims, oftentimes you will be able to deduce the truth value of corresponding standard form claims, across the square, so to speak. Right? So there's all kinds of like relationships then between these various standard form claims. So these are called, for example, the contraries. And the idea here is these can't both be true, right? So if all cats are animals, if all cats are animals is true, then we know that no cats are animals can't also be true. Can't both be true. So if we know that a standard form A claim is true, then we know that the corresponding, I should define that here in a second here, the corresponding standard form E claim will be false because they can't both be true. So what do we mean by corresponding? This is essential here. I should have started with this. Corresponding claims. We just mean that the subject and the predicates of those claims are exactly the same. They have to be exactly the same, right? So cats, if cats was the subject of the first claim and animals is the predicate of the first claim, then, right, if then the other claim corresponds to it, then cats has to be the subject of it as well, and animals has to be the predicate of it, okay? Which, in my example, was the case, right? So I said all cats are animals. If that's true, then no cats are animals has to be false, right? So given what we know, and this is the kind of thing, especially for you rookies, you just kind of have to memorize, right? That this relationship, again known as the contraries, the A and E here, they can't both be true. Okay, so if we know that the standard form E claim is true, then this one's going to have to be false, the standard form A claim. Okay? And then similar sort of thing down here with what we call the subcontraries. The relationship between the I and O. They, however, can't, it's not that they can't both be true, but they can't both be false. So if we know, for example, some dogs are cats is false, if we know that's false, then the O claim, the corresponding O claim, right? So that's an I claim. What would the corresponding O claim look like? It'd be something like this. Has to have the same classes in both, right? Or the only difference then is not. Well, if we know this is false, again, they can't both be false. Well, then we know this has to be true. And of course, I tried to use one that was, true, or that was intuitive for us, right? So we know, right, that it's the case that some dogs are cats. That's false, right? And so intuitively, if we know that's false, well, it's going to be true then that some dogs are not cats, okay? And so no matter what you put in these blanks, though, I was trying to use one that would kind of make sense because that's the case, right? That some dogs are cats, it's false. But it doesn't matter what you put in here as long as you're consistent and have hence corresponding claims. This is always going to be the case. If you know one of these is false, the other one's going to have to be true. Okay? So it's really cool. Then that's what one of the exercises you have to do is sort of deduce, at least tell what you can deduce, if anything, given the truth values of one of the various standard form claims, right? Can you then infer the truth values of the other three corresponding standard form claims? Sometimes you can't, but oftentimes you can. Okay? We also have some other relationships here. Let's see. These are called contradictories. Okay, whether you're going, as I've illustrated or have on the illustration for slide 8, both of these directions are called contradictories. Okay. And do I have all this? I guess the next few slides I'm basically going through what I'm going through now. So when it comes to the contradictories, so A and O are contradictories, and I and E are contradictories. They can never have the same truth value. Never have the same truth value. Okay? So, again, if we know a standard form A claim is true, wow, there's lots we can infer because, again, given this relationship, contradictory relationship with O, well, then we know O has to be false, okay, because they're never going to have the same truth value. Okay, if all cats are animals is true, then some cats are not animals has to be false. Okay, makes sense, right? Intuitively. And again, given the contraries, right, that relationship we already discussed, if all cats are animals is true, then no cats are animals has to be false as well, given that relationship, right? But now we're emphasizing the contradictory relationship. Okay, if A is true, O has to be false. Okay? If A is false, O has to be true. Okay? All dogs are cats, if that's false, well, some dogs are not cats has to be true. Okay? And the opposite's the case as well. Okay? No dogs are cats. Okay, if that's true, then some dogs are cats has to be false. So opposite truth value, E and I. Okay? It works the other way too. If you start knowing the truth value of an O claim, you can then deduce the truth value of the A claim. It's going to be the opposite. Or if you start with the truth value of an I claim, you can figure out the truth value of an E claim. It's going to be the opposite. Okay? So let's go ahead and go through the next few slides and make sure I covered I also talk, the picture I have on slide 8 talks about entailment. I'm not going to spend too much time in the general lecture 4 here video. I do talk more about entailment, the relationship between E and O going just this way, and A and I going just this way. In the extra lesson, what was that? Extra lesson C, where I talk about the square of opposition. But for the sake of our quiz and they don't talk about it in the chapter and homework, so you don't have to worry about it for that. So we want to emphasize and focus on these 3 types of relationships. Okay, so know those. And it seems like a lot at first, but once you get some practice and go through some of these on the exercise, it actually becomes kind of routine. So let's go ahead and move forward here. Slide 9, I talked about what it means to be corresponding claims. As they mentioned in the 10th edition, page 262 again, quote, 2 categorical claims correspond to each other if they have the same subject term and the same predicate term. Okay, so hopefully, that's ingrained now. So I give you an example. All silly dudes are crazy lads corresponds to some silly dudes are crazy lads. Again, provided that subject and predicate, whatever goes in the first blank and the second blank, as long as those stay consistent, then between the claims, right, then they correspond. They're said to correspond. Okay, and so bottom of slide 9, I just mentioned, all those ways we can figure out the truth values of corresponding standard form claims based on just knowing the truth value of one to begin with. They talk about it, as I mentioned, in the bottom slide 9. They have a nice little handy synopsis of it on the bottom of page 268 of our text. And then, yeah, I guess slide 10 is basically just, we've already captured all of those relationships then. I guess I should have mentioned, there are, and so I guess this is what you can take from slide 10, right? No, I did mention that actually. Yeah, so how, for example, they can't both be true, and these can't both be false, and then these are going to have the opposite truth values. Okay, so yeah, we did cover everything on slide 10. Let's go ahead and move forward then to the next thing we want to talk about, which also has interesting implications, and there's certain things you can infer based on these, and that's the idea of categorical operations. So we're going to need some space here, and we're going to cover 3 so-called categorical operations. And what we mean by that is there's certain sort of things you can do to these standard form claims, sort of operations, if you will, things you can do to them that result in a kind of new claim, and these operations will yield, based on sort of what you're doing, what these operations are, they'll yield like equivalent claims sometimes, and other times they won't yield logically equivalent claims. So what do we mean by, maybe we should start there, logical equivalency? Again, we just mean has the same truth value. Okay, well, if 2 claims are logically equivalent, they will have the same truth value at all times. So it will never be the case that one is true while the other is false, right? If one's false, the other will be false. So logically speaking, they're saying the same thing. Even though in an average everyday sense, what we started with might seem slightly different, logically what the person's saying or what these standard form claims are saying is exactly the same from a logical perspective. So that's what we mean with this idea of logical equivalency. So so this equals claims always have same truth value. One won't be false while the other's true, or one won't be true while the other's false, and so forth. So that's important, and it's related to this idea of categorical operations. So when we apply these certain categorical operations, what results may or may not then be logically equivalent to what we started with. Okay? So let's start. So we're going to detail conversion, obversion, and contraposition. These are the 3 operations. So, and I detail conversion then on slide 11. As they say, so we're starting with the particular claim, okay? And as they say on page 269 of the text, quote, you find the converse of a standard form claim by switching the positions of the subject and the predicate terms. So this is super simple. This is the easiest one. So here we're doing conversion. So all we do, let's say we started with a standard form A claim. To convert that, all you do is just switch them around, right? So as they say, right, you switch the positions of the subject and predicate terms. So rather than having cats at the beginning, right, you would put animals. So again, this is important too. When you perform the operation, you'll still end up with something that's in standard form, right? If you started with something that's in standard form, okay? So we converted our original claim. This is what results. And so, one of the things we want to know is this then logically equivalent? Does it say the same thing, logically speaking, as this? And it does not, right? As we point out, or as I guess it's a quote from page 269, all E and I claims, and this is an A claim, not an E or I claim, but not A and O claims are equivalent to their converses. And you can see why that's the case, right? This is not going to be the same as this, okay? So all cats are animals is not saying the same thing as all animals are cats. Okay? So they're not logically equivalent. Again, what do you do when you convert a standard form claim? You just switch around what's in those blanks. Okay, let's say we had started with, again, I want to have examples that are kind of intuitive, that kind of make sense. Okay, so let's say we started with a standard form E claim, no cats or dogs. Well, how would we convert that? Well, all we do is just switch the place of the predicate and subject. So no dogs or cats. And that is, lo and behold, logically equivalent, right? They mean the same thing, right? They indicate the same thing, logically speaking. Okay, if this is true, this is going to be true. If this is false, this is going to be false, right? And we know, right, it really is, in fact, the case that no cats or dogs, hence no dogs or cats. So the cat's conversion, I'll give you another silly example at the bottom, right? Some goofballs are silly heads. To convert that, you just switch around the positions. So you just say some silly heads are goofballs. Super simple. That's the easiest one. But then the other ones, and I should have left the square of opposition up here for this one. That's okay. The other ones are a little trickier. So let's go with Obversion here. Let's see. Obversion, there we go. So the first thing you do is you go across the square of opposition. Okay, so let's say we started with no cats or dogs. So you remember the square of opposition, right? You gotta commit that to memory, or the rectangle of opposition. A-E-I-O. So if you start with an E claim, you're going to, when you obvert it, okay, the new claim is going to be an A claim. Okay, so that's the first sort of ingredient, is you have to go across the square of opposition. Okay, or sort of another way to put it, I think they do, is you're kind of going from affirmative to negative, or negative to affirmative. So if you start, as we do here, with a negative standard form claim, E claim, you're then going to switch it then to an affirmative or positive claim, in this case, an A claim. It's probably easier to just remember, go across the square, or across the rectangle of opposition. So if you start with E, you're going to go to A. If you start with I, you're going to go to O. Right? And the second, now we need a new term here for concept, because the second criteria involved, or the second thing you're up to, involves this notion of complementary terms. Super simple concept. Two terms are complementary if and only if they capture every single possibility. So what does that mean? Let's say we started with fire trucks as a noun or noun phrase. Okay. What would be the complementary term of fire trucks? Non-fire trucks. Okay. And a lot of times it's just that simple. I don't know if you have a dash there, but something like that. Fire trucks, non-fire trucks. So again, together, these two are complementary. They capture all possibilities. Okay, so 9 times out of 10, you just stick the non in front of it, right? The complementary term of dogs would be non-dogs, right? So 9 times out of 10, you just stick non in front of it, and you'll get the complementary term. Okay, so going back to aversion, all you have to do, as I mentioned on the top of slide 12, is go across the square of opposition, and then use the complementary term for the predicate. Okay, and you just got to remember this. So the subject stays the same, but then we would use the complementary term for the predicate. Okay. So no cats or dogs. When we avert that, what results is all cats are non-dogs. Okay. What's interesting about obversion, one thing that's nice about it anyway, is that every type of standard form claim is logically equivalent to its obvert, or what results when you avert it. Okay. It doesn't matter if you started with E, A, I, or O, they're always going to be equivalent to what results when you avert it. So again, kind of make, this is the case, no cats or dogs, that's in fact true. Okay, and that when that's true, as it really is, then this is going to be true. All cats are non-dogs, right? That is in fact true, just as this is in fact true. Okay? But if this were false, so would this be. This would also be false, right? Because again, they're logical equivalent. They're always going to have the same truth value. So let's try one more. Let's go. Let's go. Some animals. Did I start? I can't remember which one. I'll start with an O here. Some animals are not cats. Okay. So we want to avert this. 2 things we have to do, right? Move across the square of opposition. So in this case, we're moving this way from negative to affirmative. So we're going to result with an I claim here. Okay. And then we also need the complementary term of cats. So the predicate or the subject will stay the same. And again, we don't have, it's not negative anymore, it's not O, it's an I claim. Some animals are non-cats, right? Because we want, we want the complementary term now of our original predicate. Okay, so we went across the square of opposition, and we use the complementary term for the predicate. So if it's the case that some animals are not cats, which it really is, right? So if this is true, then this is going to be true, because we know no matter what you start with, what results, it's going to be logically equivalent. So if it's the case, as it really is, some animals are not cats, then it's going to be the case that some animals are non-cats. Okay, hopefully that one kind of makes sense. And then we end with contraposition. Which I outlined then. What is this? I give you another example, by the way. I give you examples of complementary terms and another example of obversion on slide 12 that I'll let you peruse at your leisure. So slide 13 is where I discussed in contraposition. Okay, and again, 2 steps involved. Once you kind of get them ingrained, not so bad. So let's start with an A claim again. Let's just keep it consistent, nice and simple, and say all cats are animals. Okay. Here, as I mentioned on the top of slide 13, 2 steps involved when you try to find the contrapositive of an original claim, right? So we're performing this operation of contraposition on this original claim. Well, how do we do that? How does this work? Okay, so again, as indicated on the top of slide 13, the first thing you're going to do is switch the positions of these 2, the subject and predicate, right? So animals is going to go here and cats is going to go here. But before you do that, the second thing you're going to do, you want to note, right, is you're going to replace them also with their complementary terms. So not only do they switch positions, but they also then use their complementary terms. Okay, so we'll stay with all, and then we'll go all non-animals are non-cats. Okay, and you can get some pretty funky sounding things, right? But that's what it would look like. The contrapositive of this is this. Okay, so all cats are animals performing this operation of contraposition on it, and you get all non-animals are non-cats. And as indicated, you might have kind of noticed, right? Well, if this is true, this is also going to be true, right? If it's the case as it is that all cats are animals, well, that's going to be logical equivalent to this because all non-animals are non-cats is also true then. Okay, so A and O, but not E and I claims are going to be equivalent to their contrapositives. So this is equivalent, right? Well, let's do one that's not equivalent. Okay, so let's do, right, how about an I? So let's say some cats, how about some animals are cats? Start with that. Some animals are cats. Okay, so that's an I claim. And when we want to arrive at the contrapositive of that. So we're going to switch these places, right? So we'll still have an I claim. But then we're also going to use the complementary terms, right? So some non-cats are non-animals. And we don't actually know that just because this is true doesn't mean this is going to be true, and that's why these are not said to be logically equivalent. Okay? So, but this is what the contrapositive of this looks like. Okay? Again, you switch the subject and predicate just like you do in conversion, okay? But then, unlike conversion, you also then use the complementary terms of both. Okay? So similar to conversion, but you're doing that additional step. Okay? And then it's kind of interesting because then what's logically equivalent here, A and O, right, will always be logically equivalent to then their contrapositive. It's the opposite for conversion, right? It's E and I that are logically equivalent to what results after conversion. So in this case, again, what A and O are always logically equivalent to their contrapositives. In the case of conversion, it was the opposite. Again, I and E that are always equivalent after you convert the original claim. That's what you started, what's equivalent, logically equivalent to what results. And it's the opposite here. Okay, so we started with an I claim, not logically equivalent. Okay, it's not an A or O. So we already know, just given how this stuff works, that whatever results is not going to be logically equivalent. I'll give you another example there at the bottom of slide 13. So slide 14, definitely, let this particular slide soak in, make sure it kind of makes sense. I wanted to try to capture for you what's going on here. Basically, give you lots of examples. Some of these we went through, right, step by step with I and I already used, but you can see at a glance, right, what you start with, then what results after you perform these categorical operations on them, okay, and whether or not what results then is going to be logically equivalent. Okay, so again, slide 14, great slide. Make sure you know that idea of logical equivalency. Okay, when, after performing these categorical operations, when is what result's going to be logically equivalent to what you started with, and when isn't it? Remember, the nice thing about obversion, that second one, is that everything is logically equivalent to its obvert, or what results after you perform obversion on it. Not the case with the first and third, though. So, again, a lot here. Practice, practice, practice. Not as cumbersome or tricky as it initially seems, I would argue. Okay? It can be done. Okay, so those are categorical operations. Let's move on to another concept and talk about categorical syllogisms. This is something that Aristotle talked a lot about. A lot of this goes back to him as well. Of course, almost all of this does, but this is, he's really famous for this idea of categorical syllogisms or syllogisms. So as I mentioned, let's put this up here. As I mentioned at the top of slide 15, quoting page 278 of the text, a syllogism is, quote, a true premise deductive argument, and a categorical syllogism is going to have an even more specific type. So we know there's two premises involved in any syllogism. Of course, the conclusion, we're dealing with an argument here. And then a categorical syllogism is more specific, right, is, quote, also from 278, a syllogism whose every claim is a standard form categorical claim. Okay, remember that when we're dealing with categorical syllogisms, for everything that's about to follow, for it all to be the case, you have to have everything that's involved be in standard form. Okay, don't forget that. So, whose every claim is in a standard form categorical claim, and in which three terms each occur exactly twice, and in exactly two of the claims. So, you have three terms, again, occurring exactly twice throughout the argument, okay, and two different claims. And that sounds like a lot, but it's really straightforward. So you're going to have, it's actually pretty straightforward. So you're going to have two premises, okay, and a conclusion, obviously. I'm talking specifically about a categorical syllogism here now, not just a syllogism, okay? And they're all in standard form, okay? They have to, in other words, everything that's here has to be in, said like this, okay, in standard form. And then the terms, right, every term that appears is going to occur exactly twice in two different claims. So I'll give you an example, bottom page 15. Some students are parents. Okay. All second, so that's standard form, I claim. And then we're told all students are workers. Okay, and then the person offering this argument wants us to conclude, that's also in standard form, okay? They want us to conclude then that some workers are parents. Okay, also in standard form, another I standard form claim. So notice though, here at the outset, what we want to emphasize, right, is that these terms, we have three different terms, workers, students, parents, and they each occur exactly twice in two different claims. Students occurs twice, two different claims. Parents occurs twice, two different claims. Workers occurs twice in two different claims. So they're all in standard form, and we have three different classes represented by these terms. Classes are categories of things represented by these terms that each occur twice, okay, at some point in these claims. Okay, so moving on then to slide 16. This is really straightforward. So let's go and look at, going over here to make this point. So we have some conceptual terms we have to, again, kind of commit to memory. We have this idea of the minor term. Wow. Major term and the middle term. So you're going to have to, again, just remember this stuff. Best way to figure out and find out what the minor term is, the major term, and middle term is to start with your conclusion. The minor term is just whatever the subject is of the conclusion. So what is the minor term in this case? Workers. And again, this is, I actually cite the definition from 278 on the top of 16. So when we talk about a minor term, they say, quote, the term that occurs is the subject term of the syllogism's conclusion. So just like I said, right, it's the subject, the first blank, whatever the term is in the first blank of the conclusion. Major term, still in the conclusion. This time, though, it's the predicate. So here, you're going to be parents. Okay. This is one of the conventions that I referenced at the very beginning of the lecture that you just have to get used to and remember and follow. Okay. Make sure you have your minor term right, your major term, especially when it comes to diagramming them. Right. When we go to diagram this stuff, you want to know what the minor term is, you want to know what the major term is, and you want to know what the middle term is. And what's the middle term? Well, it's the only other one, right? It's the term or the class that's not represented or signaled in the conclusion, right? So in this case, what is it? Students, the one that does not appear in the conclusion. Okay, that's your middle term. I'm not going to, basically they just define it the same way what I just said there. And so that's what I go through and cite throughout the rest of slide 16. So on the top of slide 17, as I say on page 279, quote, diagramming a syllogism requires 3 overlapping circles, one representing each class named by a term in the argument. So let's go ahead. So remember what this stuff is, all right? Let me, gosh, I wish. Several people have commented how I need a bigger board, and I do need a bigger board because that would be awesome right now. I want to leave this up. I also want to diagram this stuff. You should still be able to see it here. So I'm going to put up here, you might have noticed, right, when we first started our discussion of Venn diagrams, we were only diagramming one particular claim. And so we only had 2 classes being represented, 2 categories or types of things. But when we're dealing with the categorical syllogism, we have 3 different claims, right? And 3 different terms or classes of things being represented. So we no longer need just 2 circles, we're going to need 3, okay? And here is where, when you're representing, right, what's being said, okay, you need to make sure you stick with the convention. So we're going to have 3 circles, okay? And when you go to diagram a categorical syllogism, again, start with the conclusion, okay? This I spell out in the middle of slide 17. So the minor term is going to go to the top left. So whatever the subject of the conclusion is going to go here. So your minor term, in this case, workers. So I'll put minor up here, though. Okay. Whatever the predicate is of your conclusion, your major term, is going to be the top right circle. And then whatever the middle term, right, whatever class of things is not represented in the conclusion, right, not mentioned in the conclusion, will be the lower middle circle, which we refer to as the middle term, representing that, again, that class of things not referenced in the conclusion. So as I mentioned in the bottom, slide 17, then, when diagramming these categorical syllogisms, we're going to employ the same kind of tactics we did when just diagramming basic, one basic standard form claim. Shading is going to illustrate exclusion, right? Not the lack of possibility that there's something there, whereas an X is going to indicate that there is at least one, if not many more, members that are in that area, right? Okay, so let's go ahead and turn to slide 18. Actually, maybe, do I want to try to go ahead and I could diagram this as an illustration for you guys to see how it works. Well, let me actually go through, because there are some tips that I mentioned in these subsequent slides. For example, slide 18, actually, one of the first things you want to note, and this is a good example to illustrate this. So I and O claims are tricky in that there may be a few places to put the X. Remember, because with I or O claims, you just put an X, right? But let's say, for example, so let's put these actual terms up here: workers, parents, students. Okay, so the issue, and what I'm referring to on slide 18, is that if you try to start here, you're going to have some trouble, because we're being told some students, so we're talking about this class of things right here, some students are parents. So we're told, hey, we know there are students that are also parents. But here's the problem. There's actually 2 possible places here, right? Because this part of the student circle would also be parents, but so would this part, right? So we don't know whether the students that are also parents are also workers yet, right? We don't know whether to put the X here, or maybe there's X's in both. We really don't know at this point. And so the whole point here is, when you're dealing with needing to put up an I or E claim, it's always best to actually start instead with any A or E claims you might have in the premise, right? In the premises. By the way, we're only diagramming or illustrating the premises, right? We're trying to map up the premises, put the premises in here, and then we step back and we ask, is the conclusion, right? Is that something we can infer just by diagramming the premises? Okay, more on that here in a second. But so the point again on slide 18, it would be better for us to start here, because maybe by starting here and shading certain stuff, we can eliminate one of the possibilities. Okay, so let's see if that, I don't actually know if that happens here, but let's see. So all students are workers. So here we're told, so again, the point is, don't start here in this kind of example. Start with this premise instead. Illustrate this premise first, okay? Because then it might reduce the eligible spots to place this X, okay? So all students are workers. So it's not possible to be a student and not be a worker. So we're going to shade out that possibility. So if you're a student, we're being told, and again, when we're analyzing the validity of an argument, we don't care if these premises are actually true. We're just going to assume they are. So if we're told all students are workers, okay, it's not possible to be a student and not be a worker. Now look what this did for us. Let's go back to our first premise and try to diagram that now. So we were told some students are parents. Before we had 2 eligible spots. Well, look what happened. By diagramming the second premise first, this A claim, now we know there has to be an X here. Because, again, we're assuming what they're telling us is true. Some students are parents. There's only one spot left where they can be a student and also be a parent. And we know there's somebody there, right? There's at least one, maybe 7 million students that are parents. So there has to be a member there. Okay, so again, in these kinds of scenarios, don't give up just because there's multiple spots. Put that X. If you have an A or E claim as the second premise, start there instead, and then voila, maybe it'll open something up for you. Okay, or maybe it'll eliminate possible spots, and then you'll know more definitively where to put that X. So we have mapped up this argument, okay, using Venn diagrams. We've represented it. So when it comes to assessing whether the argument is valid, all we need to do now, we don't do anything with the conclusion in terms of illustrating it. Okay, all we do is step back and we ask ourselves, is this indicated by our diagram of the premises? Because if you think about it, what the person's doing with the deductive argument is they're saying, if these premises are true, the conclusion has to be true. And we're saying, hey, we're going to give you the premises. Let's diagram what it would look like if the premises are true. And then we're stepping back and saying, well, okay, is what they're saying actually valid? Does it have to be the case then the conclusion is true? So we should be able to tell the conclusion then just by diagramming the premises. And we ask ourselves, is it the case, right? Having diagrammed the premises, is this shown then? Okay, some workers are parents. So let's go to the workers. Do we know definitively, right, given this illustration of the premises, that some workers are parents? It kind of looks like we do, right? Because we have an X in this spot, right? Which, right, is workers that are also parents. Maybe it was just one, maybe it's 7 million, but we do know, right, that there are some workers who are also parents, given our diagramming of the premises. So this is a valid argument. Okay? Just by diagramming the premises, just by assuming the premises are true, we see the conclusion has to be true. Right? Conclusion follows. We can see this just from the illustration of the premises. Okay? But let's say that X wasn't there, or let's say it was somewhere else. I don't know, right? Well, that wouldn't work either, right? But let's say it wasn't there for some reason. Then no, right? You wouldn't be able to infer this from just that, right? But we did have an X where workers were also parents, right? So that would be an example of a valid argument. Oh, so I did want to mention, well, what if after kind of, as I mentioned in the bottom of slide 18, what if after starting with the A or E claim, it still doesn't eliminate enough possibilities, right? So let's say, for example, you were told some workers are parents, okay? And after illustrating the other premise, you still didn't know where to put it between these 2 eligible spots. You'll put it on the line, okay? And that signals there's at least one member that's here or here. We don't know definitively where, okay? It might be here, it might be here. We don't know, and that's what an X on the line means. And so let's say our conclusion that they wanted for that argument, right, was let's say some students are parents was the conclusion. We wouldn't actually be able to infer that, right, because this X, we don't know definitively that it's here. It might be here, right? So X on the line is not enough, right, to deduce, for example, some students are parents, right? It might be the case, but we don't know enough given this, okay? So X on the line, very tricky. Be careful when you have an X on the line when it comes to trying to figure out if the conclusion has to follow given the premises. Okay, and so slide 19 again kind of gets into the nuances of those x's and how they can be kind of tricky, right? And how you need to be very careful when proceeding, and what exactly does an x there mean versus right here, or something like that, right? That means something different than an x on the line. Okay, so in their words, the authors of the textbook, page 282, quote, an x on a line indicates that the x belongs in one or the other of the two areas, maybe both, but we don't know which. So when it comes to determining whether the conclusion is a valid inference, as they say, quote, we look to see whether there's an x entirely within the appropriate area. An x partly within the appropriate area fails to establish the conclusion. Okay, and I tried to sort of show that a moment ago. Also from the textbook, page 280, quote, a syllogism is valid if and only if diagramming the premises automatically produces a correct diagram of the conclusion. And so that's what I was saying earlier, right? You don't actually do anything, right? You don't diagram the conclusion. You diagram the premises, step back, and then ask yourself, okay, is the conclusion shown given our diagram of the premises? All right. Let's go to slide 20. All right, so that's right. So there's this unique situation where you have, I wish I had come up with an example beforehand, but so basically the unique situation is when you have for premises, right? You might have just A or E claims for the premises, and then your conclusion is an I or O, right, which requires an X to be placed somewhere. But in diagramming the premises, you won't have put an X because these are just A and E claims, right? So that's what I'm talking about on slide 20. As I point out there, so let's say O, S, R, P, no, P, R, Q, some, S, R, not Q. I have no idea whether it's valid or invalid, just throwing stuff up here right now. So we'll see what happens here. So this is illustrating the example of how it can be tricky, right? When you go to use Venn diagrams on this, because in diagramming these, the premises, you're only going to do shading, you're not going to put an X, but then the conclusion requires you to have an X up there somewhere. So as they point out, look, don't automatically render it invalid. Okay, we'll see in shading the premises if it only left then maybe one possible spot. So let me throw this up here. So remember, what are these three circles? We have the minor term, which is the subject of the conclusion. So we'll have S there. The major term, which is the predicate of the conclusion, Q. And then we have the middle term, the one that doesn't appear at all, right, in the conclusion, but appears twice in the premises. So let's go ahead and diagram these premises. All S or P. It's not possible to be an S and not also be a P. So all S or P is going to look like this. So if it's an S, it has to also be a P. No P or Q. It's not possible to be a P and also be a Q. So if it's a P, it's not a Q. So based on assuming these premises are true, does this have to be the case? Is it the case that some S are not Q? Well, if all we thought was like, hey, I have to see an X somewhere, this actually is a perfect example to illustrate this. Right? You're looking for an X. I don't see an X. Invalid? No. Right? Because remember I mentioned this like 30 minutes ago at this point, right? But another assumption we have, a convention that you just have to work with, right, is that these are not empty. All of these classes or categories, there's at least one member. Okay, and so what that enables us to do then, why that's important to note, right, that's an underlying assumption, is that we know then there's no other spot. Look at S. There's only one spot for anything to be a member of S. It's right here. There's only one possibility. So go ahead and put an X there. If there's only one spot left, given our assumption, right, that nothing's empty, that there's always a member of every class or category that we're talking about, you can put an X there then. Okay? Well, look what that ends up doing for us. Let's go back to our conclusion. Some S are not Q. Lo and behold, in fact, it turns out all S are not Q, which means that this is also going to be true, right? Or no S or Q, I guess would be the standard form way of saying that. But that is the case then, right? And in diagramming these premises, this shows up to be also true then, right? So this is valid. So again, when you have premises that are all A or E claims, do all the shading, and if there's any cases or circles where there's only one eligible spot left as a result of the shading, go ahead and put X's in those spots. And so actually, you know there's an X here too, right? Because there's only one area left for the Q's to be. Okay, and we know that category of things is not empty. There's at least one member there. Okay. So that's slide 20. Almost done. The last thing we want to talk about, I think, yes. Okay, the last thing. And again, I have extra lessons on all these things that we've talked about. And then also this last thing we'll talk about. And that is the rules method. So we've talked about categorical syllogisms. We talked about how to illustrate them with Venn diagrams, and then how to assess whether the categorical syllogism is valid or not using the Venn diagram, right? Illustrate the premises, and then ask yourself if the conclusion has to be the case given the illustration of the premises. Well, there's another way we can assess a categorical syllogism, and that's known as the rules method. So we're talking about the rules method for assessing categorical syllogisms. So as I point out in top slide 21, so in addition to Venn diagrams, we can also assess these categorical syllogisms via the rules method. It's founded on two key concepts, one of which we've already talked about, affirmative and negative. Okay, so hopefully that's kind of making some sense to you. Now we have this other concept I briefly mentioned way earlier in the video that these squigglies meant something. Well, this is what they mean. Okay, this is where I'm referencing that again. Okay. So in order to do the rules method, we have three rules. We'll have those in a moment. We need to be comfortable. There's two concepts involved in these rules that we need to be comfortable with. And everything's actually indicated right here. The idea of affirmative and negative claims, and then also the idea of distribution. Okay. So more on that here in a second, but I just wanted to point out these squigglies are indicating when something is distributed. Okay. And so if it's just a regular blank, that means it's not distributed. So this term is distributed, this term is distributed, 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 not distributed, not distributed, not distributed, not distributed. So what is that, 4 and 4? 1, 2, 3, 4, 1, 2, 3, 4, yeah. So what is this idea of distribution? As they define it, the authors of the textbook on page 289, quote, terms that occur in categorical claims are either distributed or undistributed. Either the claim says something about every member of the class the term names, or it does not. So the idea is the terms, it's like an on-off switch, right? It's either distributed or it's not. Okay, when is the term distributed? Well, it's distributed if, given what's said, we know something about every member of that class. So going to an A claim, the idea is, look, if we're told all cats are animals, we know something about every cat. Namely, it's an animal, right? So the term cat is distributed, right? We know something definitively about all cats. Same thing if we're told no dogs or cats. Both those terms are distributed. We know something about all dogs and we know something about all cats, namely that they're not one another. Right? And the trickiest one is the predicate of an O claim, right? So if we're told some animals are not cats, we do know something about all cats, namely they're not the some animals that aren't cats, right? That's the trickiest one to kind of understand, but in general, the idea is, right, terms distributed if, given what's said, you know something definitively about every member of that category. Right? So let's go back to A and talk about why this is not distributed. All cats are animals. We don't know anything definitively about all animals, given what's said there, right? Like we do about all cats. So remember, all cats are animals. We know that every cat is an animal then, right? But we don't know given what's said there, that every animal, we don't know anything definitively about every animal, given what was said there. And if some animals are cats, right? Or let's see, let's do, yeah, so some fire trucks are red vehicles, let's put it that way. Or I almost said some fire trucks are red, but that wouldn't be good enough, right? So some fire trucks are red things, right? Or red vehicles. We don't know something definitively about either one of those. So just because some fire trucks are red vehicles, right? We don't know anything about all fire trucks, and we just know that some of them are red vehicles, that is, right? And we don't know anything definitively about all red vehicles either. We don't know that they're all fire trucks. We don't know that they're all not fire trucks. We don't know anything definitively about either of those terms in the instance of an I claim. So hopefully that idea of distribution is kind of starting to make some sense. So if you have the notion of affirmative and negative claims in mind, and then also this idea of distribution, well, then you can apply these three so-called rules, okay, for the rules method. Oh, I should say, so slide 22, basically I'm just, at the top there, I just kind of represent again the standard form claims and, what's distributed and what's not, and talk about how the O is a little bit trickier. So moving on to then slide 23, where I actually articulate the rules themselves. Okay. So what is the first rule? It's the most straightforward. I should let me put up an argument here, and I'm just going to throw one out here. Let's go with all cats are lazy creatures. No lazy creatures are awesome creatures. Sorry, all you cat lovers. We've had plenty of cats in our history, so nothing personal. And let's say the conclusion is, I don't even know so what do I need here? No awesome creatures. Remember, for a categorical syllogism, we need every term to appear twice. Okay, so what am I missing? Are cats, maybe? Cats. Sorry about the handwriting again. I'm going to say these out loud. So all cats are lazy creatures. No lazy creatures are awesome creatures. And so they want us to conclude no awesome creatures are cats. Okay, so that's a categorical syllogism. Everything's in standard form, right? And every term appears exactly twice in two different claims. So we could, and maybe I will afterwards, do a Venn diagram of this and then assess it using the Venn diagram. But there's this alternative method known as the rules method, right? And so you need to have so the first rule is, and you need to have these rules in order, right? So when you're doing the exercises and you're identifying which rules are broken, when you say rule 1 is broken, you need to mean this specific rule, okay? And again, that's the convention. You just need to go according to that, okay? So you need the same number of negative claims in premises as conclusion. So right off the bat, you know that if you have two negative, right, claims as premises, it's got to be invalid, because you can't have more than one negative claim as a conclusion, because you only have one claim as a conclusion, right? So, but if there's no negative claims, right, in the premises, then there better not be a negative claim in the conclusion. So it has to be the same. And let's see, right, if that actually happens in our example. Is rule 1 satisfied? It is, right? We have one negative in the premises and one in the conclusion. Okay. The second rule is let's put it that way. At least one premise must distribute. Good grief. Distribute middle term. Okay. So let's see if that happens. The middle term in this example is what? What doesn't appear in the conclusion? Lazy creatures. So we need to find out if at least one of these premises distributes lazy creatures. Okay? So let's start here. A, this is an A form, standard form A claim. Is lazy creatures distributed? Well, it's the predicate here. We know the predicate is not distributed in a standard form A claim. So not yet, but what about the second premise? Is it distributed here? Well, in any E standard form claim, both terms are going to be distributed, and it does appear there. So at least one premise does distribute the middle term. Right? And the last rule is that basically anything that's distributed in the conclusion has to be distributed somewhere in the premises. So anything distributed in conclusion has to be distributed in premises. I don't even know why I bother writing that because you probably can't read it. But again, so that says anything distributed in the conclusion has to be distributed in the premises. So let's go to our conclusion. And in an E claim, they're both distributed. So now we're going to have to go to the premises and make sure that both of these are distributed somewhere in the premises. So let's look at awesome creatures. Awesome creatures doesn't appear in the first premise. It appears here. Also an E claim, so we know again that it will be distributed because both terms, subject and the predicate term, are distributed in E claim. So awesome creatures is distributed in the premise. What about cats? So that's good. Since cats is also distributed in the conclusion, it better be distributed somewhere in the premises. And it is, right, because it's the subject of a standard form A claim in the first premise. So, so yes, it is also distributed in the premises. So we actually satisfied all three rules. And the idea then is so long as none of these are, as long as all of these are met, right, then it's valid. Okay, if at least one of these is violated or not satisfied, right, all you need is one, and then it's invalid. Right? And so like on your homework, on a quiz or whatever, it might be the case that more than one is not satisfied, in which case you need to indicate which of the rules, right? Don't just tell me a rule is violated. Well, which ones? Right? Maybe it was all three, right? So you need to tell me one way or another. So we know this is valid. Let's see real quick what the Venn diagram looks like for this. So we have two different tools or methods we can use to assess the validity of a categorical syllogism. Okay, so we're going to put our circles up here, go to our conclusion, figure this out. So awesome creatures is the minor term. I'm going to say AC for short. Cats is the major term. Okay, so it goes over there. Middle term is the one that doesn't appear. Is lazy creatures, LC for short. Okay, it doesn't appear in the conclusion, that is. So let's go ahead and map to diagram our premises. So premise one, all cats are lazy creatures. So it's not possible to be a cat and not be a lazy creature. Okay, so any cat is going to also be a lazy creature. No lazy creatures are awesome creatures. So if it's a lazy creature, it's not possible to be awesome. So we're going to eliminate those possibilities. And so, given our diagram of the premises, is it true that no awesome creatures are cats? It is. Any place where it would have been possible to also be a cat has been shaded or excluded, right? So this does follow, right? It is implied given the illustration of the premises. Wow, I think that is it. A lot there. I know we've unpacked a lot. So keep in mind, again, those extra lessons. Extra lesson A, translating into standard form claims. I'll give you a lot of examples. Extra lesson B dives into much more detail with Venn diagrams. Extra lesson C outlines in much more detail the relationships between the standard form claims on the square of the opposition and what we can infer from that, right? Knowing the truth values of one type of standard form claim, what we can infer about the complementary, or corresponding claims then on the square of opposition. And extra lesson D deals with the categorical operations, conversion, conversion, contraposition, and again gives a lot of examples working through those. And then finally, the extra lesson E goes through this in much more depth, offer several examples once more. So a tricky chapter for sure, a lot of tricky material here, but not something that's unmanageable, not something that can't be conquered, if you will. And in fact, it really does become, the more practice you become, the easier it really does feel. Now there are, again, lots of tricky exceptions and weird nuances sometimes, but if you can just, I think at your level, right, just memorize certain aspects of it to start off with, as long as you can, and again, those building blocks, those basic building blocks we start with, have a firm grasp of, these standard forms, for example. As long as you just get some of that ingrained, again, going through then and using the Venn diagrams to assess categorical syllogisms, a lot of that then follows fairly easily. I say that hesitantly, I guess, but anyway, that is the end of lecture 4. So lecture 5, we will stick with deductive arguments, but we'll turn our attention to truth functional logic, like a different way of approaching what someone's saying to us in a deductive fashion, and a different way of analyzing the underlying truth functional nature of what they're saying. Okay? So that'll make more sense, obviously, when we talk about that in lecture 5. But that's what you have to look forward to. Again, make good use of those extra lessons I've been referencing. So we unpacked a lot here. Otherwise, I look forward to lecture 5. Good luck with the homework. Again, chapter 9 homework, if you're taking the course that's associated with lecture 4 material that we just discussed. Thank you.